Hello, is my microphone on? Well, I want to thank the organizers for the invitation to come, and I'm very happy to find there's still interest in this project that I've been working on for a while, but has existed probably since the 80s. I started this project when Clarence Shutt came to the University of Toledo and gave a seminar on the topic, and I was the first person he met on his seminar series of talks with all the faculty. And that's quite honestly how I got hooked into the fascinating diffraction pattern from profillinactin crystals. And this is a fairly old project. I believe a lot of Shutt's papers are in the 80s. I believe Gerard Bracon himself told me once he collected data on the semicrystalline state of profillinactin. So I'm going to try to tell you how to deal with these aperiodic protein crystals. And I wanted to give tribute right away to my then graduate student, Jason Porta, who actually got his PhD in 2011, which kind of surprised me when I looked that up last night. And the other work is from Jeff Lovelace, who is what I'm calling a lab lifer. He's worked for me for 25 years. He's supposed to be here right now. He was supposed to give a poster, but unfortunately, on the first day of the year, he told me he was too sick to travel. And so any technical questions, you need to email Jeff. So what is an aperiodic crystal? Well, there's really three categories. The first is these quasi-crystals that have these really funky, like five-fold symmetry in their diffraction pattern. They're quite beautiful. And the second would be composite crystals, which are really like a sort of material type crystal. And then there's the ones that we work on, which are these incommensurately modulated crystals. And as I said, we've been working on this since 1997, developing protocols and concepts for applications of what are really small molecule approaches to protein crystallography. So I'm going to start off telling you how what I mean by a modulation in a crystal, and how this modulation will affect the diffraction pattern of the protein crystal and the structure. What's really happening is that there's a loss of translational symmetry within the crystal, but there is some order to this loss of order, and that accumulates into what are called satellite reflections around either side of a main reflection. So there's some movement in the crystal that causes this, and it's really, so what in the end, we're really looking at protein dynamics within the crystal. So I have some examples, and then I'm going to tell you about how to process the data using something called a Q vector. So normally we assign indices to our reflections in 3 dimensions, but with this type of crystal, you have a 4th, and in a small molecule crystallography, you can have in a 5th or a 6th dimension in your diffraction pattern. But we only have 4, so we're doing good. And we use eval15 to process the data. And there's these things called superspace groups, which I wrote an article just on that topic, and I won't go into it much for this talk. What we end up doing then is we figure out all this 3+1D dimensional space in the crystal, and then we end up going back into 3D space to solve the superstructure. And we start with an average structure, and we go into make a commensurate superstructure that will approximate what's happening in these crystals. Finally, I'm just going to briefly mention some future work that still needs to happen, which would be to fully solve one of these structures, not using any approximation, but to actually use a superspace refinement. And to do this, each atom of the structure would be assigned a modulation wave, okay, for a final refinement that would be an accurate refinement of these structures. I propose that we should combine IANA 2006 software, which is a software package out of the Czech Republic, with RefMac, and merge those together to actually do this sort of refinement. And so far that hasn't happened. So I will not talk any further about that today. So what is a crystal modulation? So say here, this would be what a periodic crystal, really simplified periodic crystal looks like, where hopefully every unit cell looks the same. You have the same structure in every unit cell. But aperiodic crystals really have a long range order, but they don't have this perfect translational order between each unit cell. And they can be commensurate or incommensurate. So what does that mean? So a commensurate modulation, imagine your university builds a new building, they connect it to an old building, and the floors match, okay? You get off on second floor in the old building, you can go into second floor in the new building. Now, incommensurate modulation, like some of our buildings, the old building, the second floor is maybe 2.5 into the new building, or 2 and 0.66667, right? So that's kind of how I look at it sometimes. So here would be a commensurate modulation. So there's a translational positional change in the protein structure. And in this case, it follows a sine wave that repeats every 4 unit cells. And since it repeats perfectly every 4 unit cells, we call it commensurate, okay? These types of modulations can be solved as a supercell, right? Where you just extend one cell dimension times 4, and then you can solve it as a superstructure. So you're just stuck solving a larger structure than you would normally. Now for the incommensurate cases, which is what happens with the profilin-actin crystals, it doesn't perfectly repeat over a nice integral number. So in this case, it's kind of close to repeating over 2/7 unit cells, but not exactly. And so that's what makes it incommensurate. The Q vector here is 0.2853 and then keeps going on with other numbers, right? So it's not a nice even modulation. And that's called an incommensurate case. So we can reinstall the order into these crystals by using some superspace concepts and using modulation functions to describe the crystal. So the first question, and then this is kind of fun because you guys all been talking about whether or not people look at their data or not, right? So I spend a lot of time looking at our images, and so it's kind of like I'm old school, I guess. So let's say we had diffraction data set, and normally you would have normal diffraction that you would describe with the Miller indices in that equation right there with A star, B star, and C star, with a Miller indice in front of each one. So in a modulated crystal, you'd have those main reflections, but also have these satellite reflections that in this case are off axis. And in order to, so normal integration software will just completely miss those reflections. And so in order to index them and predict them, you need a Q vector. So in this case, the Q vector involves A star and B star, right? So you'd have some number in front of A star and B star to describe the Q vector, and C star would have a 0 in front of it because it's just along A star and B star. So you would add this Q vector to the Miller indices. And the index for the satellites, so you have H, K, and L for the main reflections, and you have an M for the 4th dimension, okay? So here, in this case, the order of M goes from up to 2, so you'd have plus 2 to -2 for the M index. So the final description of the location of the reflection is given by this equation, which has the Miller indices plus M. So the satellite reflections have non-integral HKL values, and that's what the fundamental problem is with the diffraction pattern. So we can have different types of Q vectors. So this is sort of like the case we have for profilin-actin, where we only have one satellite on either side, and the Q vector is along B star. But you could have, like I was saying, one that's kind of cattywampus to any of the unit cell dimensions, or you can even have 2 Q vectors, or you could have 3 Q vectors. I've only seen that in small molecule crystallography. So people always ask me, how many of these types of crystals have you ever seen? And I used to spend a lot of time giving talks and asking anybody if they'd ever seen any crystals like this. And people come up and say, yeah, in the appendix of my thesis, there's one diffraction image. And then that crystal was crap, so we threw it away and didn't work on it. Okay, so if you know of any, I am still interested to hear about it. I've heard of about 11 so far. So here's our protein we're interested in. We're looking at the complex of profilin with actin. Now, actin is a very abundant eukaryotic protein. You know, it makes the actin filaments in the cell. It's really involved in almost all cellular motility, from how pathogenic bacteria can swim to how metastatic cancer cells can travel in your body. And so it's involved in all those processes. It's very important. Profilin is the protein that sequesters actin and then delivers it. So it sequesters it so it won't make a filament and then delivers it to a growing actin filament. So it's really involved in controlling the growth of filaments. And actin, which is the light blue structure here, has four subdomains. 1 and 3 are the large domains, and 2 and 4 are the smaller domains that move. And it's also an ATPase. So most everyone anymore uses recombinant proteins in their studies, but we actually, Jason, my graduate student who was nice and naive and had no idea what a crazy project I was giving him, learned how to purify profilin beta actin from calf thymus. So he went to the slaughterhouse and actually ground up calf thymus to make the protein and purified it. And these are what our crystals look like. They grow straight out of a phosphate buffer, and they just grow spontaneously, no seeding. So then we purposefully modulated the crystals. So normally they're periodic crystals, but you can do things to them to make them to be modulated. One of the things you can do is to alter the pH. Usually if you go acidic, make it slightly acidic, the diffraction pattern will become modulated. So we did that. The first time we did it, it lasted for 1 frame because radiation damage just made it go back to a periodic state. So then we decided to use acidic glutaraldehyde solutions and actually cross-link the crystals in a modulated form and collected 360 degrees of data off of that baby once we got it. So my postdoc at the time, she said, "You're happy about this diffraction pattern?" And I was like, yes, I'm very happy about it. And then an even better day was when we actually indexed the reflections using eVol15. So this first one we collected has a modulation that repeats two times for every 7 unit cells, approximately. Not perfectly, but approximately. It has a Q vector of 0.2829. So if I think you take 2/7, you get 0.285, okay, so it's not a perfect approximation. Then the other one that we did, we messed around with the calcium concentration and put it in a D-glucose solution and collected cryo data at home. And that's actually our best data set. It diffracted at 2.3 angstroms. It has a different Q vector of 0.27. And that's very close to 3/11. So in more recent years, we've gone into trying to solve that one using supercell refinement. So as I tried to mention, I like to give a plug to eVol15 because it's the only software I know of that can handle this type of data. So here's some of the data from profilin actin that we get. If you do a peak search and figure out the unit cell dimensions, you'll get what we call the main cell, which for these crystals are with the open form of actin, profilin actin. But you see, when you do that peak search and do a prediction with the main cell, you're missing a lot of the reflections. So we thought, you might think, say, in the old days when you used to do this by hand, you would think, oh, maybe my crystal's mosaic. So you can increase the mosaicity here. I increased the mosaicity to 2 degrees. And you can see we still don't predict all of the reflections. We're still missing some along the B star direction. So I think you can see right where I put the blue arrow, there's 2 satellite reflections on either side of that main reflection. So it's not that it's mosaic. It's not that there's really a larger unit cell that I could try to index the data with. So like purposely make B star, allow it to be larger, right? It still will not ever index all these reflections. And you need a Q vector to do that. So once we got all of the data integrated, and in today's standards, this took a really long time, okay? But then James Holton's name keeps popping up, but he helped us make a simulated precession photo of our modulated data. And I wanted to just look through this simulated data quickly to show you how these satellites work out. So our modulation is really along B star. So when you look at the H0L precession photo, okay, this is a simulation of an H0L plane for these crystals. But if you look at this data, it looks normal, right? So in this crystal, in this dimension, there's no satellites. And I just zoomed in a little bit, just normal diffraction. And along the L direction, you can see that there's systematic absences. And along the H direction, there also are systematic absences. Now, the data really fills in if you look at the OKL part of the data, okay? So you see all these amazing number of satellite reflections that we collected off of this crystal. So if I'm gonna zoom in on this area here, I think you can see that, I'll give us a little help. I circle in blue. Here's a situation where there is actually not even a main reflection, but there's only satellite reflections. So the satellites are so strong that they extinguish the main reflection. In red here are just some other satellite reflections around their main, but you can see that even the 2 satellite reflections are not even of equal intensity around the main reflection. And then sometimes there isn't even a satellite reflection at all, depending on where you are in reciprocal space. When you're working with these data, you have to still look for systematic absences because we're trying to figure out a space group for this. So if we look along L, and I put little red circles where the systematic absences are. So every other main reflection is missing, right? Because we're going back to crystallography 101 here, okay? Then if you look along K, which is the direction of our major direction of modulation, you can see that not only the main, but also every satellite is missing. For every other one of them, right? So it's not just the main that's missing, it's also the satellite. So this is what you go through to determine a space group, right? And for our case, we're actually determining what's called a superspace group. And so from the data, I put it down here on the left, that the superspace group turns out to be number 19.1, okay? P212121 with 1 modulation direction. So there's 65, we're always lucky in protein crystallography, there's only 65 space groups. And so we're even luckier if you start adding dimensions to your space group, there's only 135 3+1D space groups. And I went a little crazy on this and actually wrote a paper about that too. So here's how we're gonna solve the structure. So this is just a pathway for a normal molecular replacement structure, right? So you have periodic diffraction data, you index it with H, K, and L. You solve the structure by molecular replacement. and do model building, going back and forth with Coot, doing your little song and dance that you do looking at your data. So we do something similar now for our approximation for the superstructure, but our data is aperiodic. We have main reflections with satellite reflections. We use Evol15 to index and integrate the data. Getting what that Q vector value is really important for solving the structure later on. And looking at the space group is very important. So the next step is we go backwards and we take the main reflection and we add to it the intensity of the satellite. So we sum the satellites to their main intensities, okay? And we use that to solve what would be the average structure. So for the whole superstructure that's forming in the crystal, we will solve an average structure, and we do that by summing together the satellites with their associated main. And then after that, we will re-index all the diffraction pattern into a three-dimensional diffraction pattern. So we remove the Q vector from the diffraction data, put it into a three-dimensional data set, and then use regular crystallographic programs to solve an estimation of the structure. Okay, so this is really an approximation. It's not the perfect, great structure we'd like to have, but it's what we can do with the software we have. So here's just that ribbon drawing of, or alpha carbon trace actually, of profilin actin with the different parts labeled. Now, if you take the average structure and look at the electron density, it looks like this. So we have really nice electron density for profilin. Excuse me. And we have really sparse data for domains 1 and 4 of actin, right? And the reason for that is because domains 1 and 4 are the ones that are really moving in the modulated structure. And even if you look at the periodic structures that we have solved in my lab, there's a lot of movement in those domains anyhow. So they're kind of disordered. And when the crystals become modulated, they really get even more disordered. Okay, so I'm waving my hands around, right? But so that's where most of the modulation motion is occurring, is in those two small domains, and also the entire protein moves around. So we're going to make a commensurate supercell approach or an approximation to get the structure. So when we go to this step of the structural solution, we drop the difference between satellites and mains, and we just consider all the data to be like normal data. And in order to do this, we end up creating a whole bunch of absent reflections to fill the space in between the satellites. I have an example and I'll show you. So we end up then with a large unit cell with lots of copies of the molecule in the asymmetric unit. And this ends up being just an approximation, but I think it answers the question of what's going on in these crystals. And so I think that'll be sufficient for the study. So in order to approximate a rational Q vector, there's a little trick that I learned from Sander van Smalen, who is a German small molecule crystallographer. Like if our Q vector can be estimated as 2/7, then we can re-index the reflections using the rule right there. So H stays the same, but K, we do a little bit of math, and L stays the same. So if I have, I'm going to show you how we re-index for one of the cases, how we actually re-index the data. So normally I have a main reflection with 2 satellites, right? So the main has the M value of 0, and the satellites are plus and minus 1, right? And in the diffraction, so in the for 4 indices, those would be H0L with 0 for M, or H0L minus 1, or H0L plus 1, right? And so it goes on. And you can fill this in. with say 3 main reflections with 6 satellites. So to re-index these in 3 dimensions, we do the little bit of math on K. So if K is 0, then 7K plus 2M becomes 2. So that top satellite becomes H2L, and H0 and H minus 2L, right? Fascinating stuff. So then you can fill in the whole thing, and trust me, this is not done by hand. And then we have to fill in all the absences. And there's lots of absences. So there's more absences than there are reflections to do this little trick. And this is part of the problem, actually. So this is basically how we re-index the data. So we take this 4-dimensional data and put it into 3 dimensions. Okay, and so we then build a supercell to approximate the structure. So along the B direction is 7 times larger, and give the average structure to RefMac and do refinement. So this would be our one data set that has a Q vector of 2/7. And this is the structure for the one that's 3/11. So when you have an odd number in the numerator, you have to go to P1 for this space group. So Jeff has been working on 44 profilin actin in the asymmetric unit for this one. So then what we do after we get done with the refinement, making a long story short, we then do a overlay of the center of mass for the molecules to try to see what the modulation is doing. And so if you look at the top right overlay, you can see that the profilin really isn't moving much. On average, it's only like 0.5 angstroms that the profilin is moving. But the small domain of actin is moving as much as 5 angstroms in the modulation. And if you make a movie of it, it looks sort of like this. And there is movement of the 2 domains coming together as actin is opening and closing in the modulation, but the whole molecule is actually moving. So this is the dynamics going on in that 2/7 modulation. And then this is a rough draft of what's going on over 3/11. I don't know if you can really see it very well with the display, but this is just an alpha carbon trace looking down C or looking down B or looking down A. If you look at down A, which I think you see the majority of the motion similar to the previous one, you see the whole thing moving, but there is a twitching between the 2 domains as opening and closing. And actually, if you zoom in on the ATP, that little bugger is moving around quite a bit. And if you just graph the center of mass for all the molecules, you get this nice modulation function for the center of mass in all 3 directions. So it really is what's going on in these crystals. So to summarize, our recent refinements really kind of have what we would call an unacceptable R value, right? They're in the 30s. And so we're still trying to work on getting that down. We need to actually reintegrate the data in P1. And then we are actually trying to figure out if there's a better way to how to deal with all those absences. Right now we're putting in zeros, which might not be the ultimate way to do it. And those things are making our R values large. We'd like to resolve the density in the large loop better. And we'd really like to publish this and put it to bed. So I just wanted to finish up. This is a picture of my lab in 2009. I'm in a striped shirt with long hair, okay? And Jeff and Jason, I have put circles around their heads. So Jason graduated in 2011. Here's my lab now. You see Jeff is still here. And I got a new retaining wall in my backyard, and they're all sitting on it for a lab picnic that we had. And that's all I have, and I'll take any questions if I have time.